Welcome back, ladies and gentlemen. I gotta tell you, I got a system for conservation. So let's look at this. We have this this ball, and then I'm gonna drop the ball. I'm just gonna release it, let it go, and of course it's going to fall to the ground. All right. So we're gonna analyze the situation because we need to try to figure out if we can successfully determine when is mechanical energy conserved. So we have ME. And also, when is total energy conserved? Just the capital E, right? And is that going to be conserved, or is that going to be conserved, or both, or neither? We're going to figure this out. That's the plan. So one way to analyze a system, and to even just define a system, is with the system schema diagram. So at the ball, we know the ball is interacting with the entire Earth. That interaction is the gravitational force. All right. And the ball is bumping into a bunch of air molecules as it falls. And so it's interacting with the air. And I know quite often we say, oh, we're just going to ignore air resistance and the force of drag. Well, what if we don't? Then let's see if we can figure this out. One way to define the system is just to put the dotted line around the ball. That's the object we're mostly concerned about. If we do it there, then we can't define the gravitational potential energy that it would have in the beginning, that we want it to have. So what we're going to do is we're going to define the system to include the entire Earth. That means we can define the gravitational potential energy that it has in the beginning. Potential energy, gravitational. Of course, as it falls, it's losing gravitational potential energy and it's gaining kinetic energy, right? So we're getting a conversion of energy from one kind to the other. And why is that? Well, there's a force doing work on the ball. The force is gravity doing work, converting from potential to kinetic. But look at this thing right here. So on a cold winter morning, warm your hands up a little bit. It's the friction that is creating the heat. And so air resistance, this force of drag, essentially you can think of it as friction with the air. There is some heat created along with the kinetic energy. So what we see is that some of the potential energy becomes kinetic, some of the potential energy becomes heat. And the way we have defined the system is it's such that we kind of can't include the heat in the system. So what's going on? Well, there's this external force. This drag is coming from something that is outside of our system, the way we've defined the system. And all right, so then the heat is not part of the system. And this should be a big, big clue. So let's ask ourselves, is mechanical energy conserved? Question mark. Well, what can we say about this? There's one big, big reason why it's not conserved. See that thing right there? That external force. That's the reason why. We have an external force doing work on the system. That's why. All right. And whenever you have an external force doing work, then the energy of the system is going to change. And so the energy here is just potential kinetic, so it's just mechanical, so the mechanical energy will change. Now the next question, how about the total energy? Is the total energy of the system conserved? All right, E, there we go. And the answer here is no, it is not. And essentially for the same reason. This external force doing work on the system, changing the energy of the system. And since I was able to list the energies, look at this. This thing right there. All right, there. We've got energy leaving our system, becoming heat, but it's leaving our system. And so, essentially, because we have an external force, so for the same reason as before. But we're allowed to define the system almost any way we want. Now, some ways are useful, and there are probably many ways of defining the system that are not useful. So I'm going to look at a different way of defining the system here. So I'm going to redraw ball, entire Earth. That's a gravitational interaction right there. I'm going to draw an air, and that is a drag force interaction. This time, I'm going to define the system this way. I'm going to include everything. The ball, the entire Earth, and the air is now part of the system. Okay, well, I'm going to ask myself the same questions. Is mechanical energy conserved? Question mark. And what do you think? Do you think, well, so there's no external force. We've taken care of that because now that force is internal. It's inside the system. That force is inside the system. But no, it is not. And it's for a reason that I hinted at over here. What are the energies that are going on? Well, the energies are, we are starting with a lot of gravitational potential energy. The ball gained kinetic energy, but things are also heating up. So some of that potential becomes kinetic, and some of it becomes heat. We can include all of these in our system, so there's no energy leaving the system. That's a clue. But think about this. Mechanical energy. Mechanical energy is just these two right here by themselves. By definition, that's our mechanical energy. And look, we still have some energy leaving the mechanical box, if you will. So, no, because of heat. Heat is generated. Heat is created. And some of that potential energy does not become kinetic. And so, no, mechanical energy is not conserved here. So really, I mean, think about that. Anytime there's air resistance, mechanical energy is not conserved. But what about total energy? Let's see. Is total energy, capital E, conserved? Question mark. Well, look at this. We have energy that's leaving the mechanical box, but do we have energy leaving the system? The answer is no, we don't have energy leaving the system. We don't have energy entering the system. There's no force coming from outside of the system. There's nothing else interacting with the ball. So, yes, total energy would be conserved here. The heat is just another form of energy. And so we had gravitational potential energy, we have kinetic, and also some heat. And even though it's transforming, it's becoming a different form of energy, it's still part of the system, the way we have defined the system. So that's it. Now, the big question really is, perhaps, when can we ignore air resistance? When is work done by this force small enough that it doesn't matter? So, put this at the bottom of the page. I think I got room. Let's see if I can make this work. Now, so can we ignore air resistance? Question mark? Okay, so the answer is no, comma, if three things are true. Or any one of these three things are true. And they're kind of easy to remember, and it's just a generalization. So please, these are not absolute rules. Don't fall into that. Because someone's going to make an argument, well, it's this or that. I'm not here to make an absolute rule or scientific law. This is just for our practical purposes. If the object is very light, very large, or moving very fast. then the answer is no. We cannot ignore the air resistance. So sometimes, of course, we're going to have to say, yeah, look, we're going to pretend it doesn't matter anymore. But sometimes we're going to have to acknowledge that air resistance might actually matter. And hopefully this helps you understand when is mechanical energy conserved or not. Mechanical energy is not conserved whenever air resistance does matter, but total energy could be conserved or not, depending on how you define the system that you're talking about. Okay, thanks for watching. I'll catch you next time.